First of all, hopefully you've noticed by now that you get a slight reprieve on homework. So we had the exam, and then this lecture is starting the new stuff. And I decided one lecture, I could ask you a few questions, but we'll only get like partway through it, one chapter. So I blew it off. And so your homework on this new material won't be due till 24th, Sunday the 24th. So we're starting chapter 13 on liquids today. You have no class Monday, it's President's Day. I won't be here. And then we'll finish 13 on liquids Wednesday and start gases, chapter 14, and finish it Friday. So we're going to do chapters 13 and 14. I kind of sum them up as fluids. A liquid and a gas are both a fluid because they can flow. And they're very similar and related. And these two chapters, I think more than the others, kind of cram in lots of little concepts. So I'm going to isolate them and just focus on that. So chapter 13 and 14 will be a unit. After that, we'll have another exam on that before I try to shove more down in there.
The door is locked over there. Do you mind opening it?
This door?
The outside door.
Oh, nice for security. I can't unlock it, but I can open it. Prop it open. So, chapters 13 and 14 this week and next week. Then we'll review the following week and have an exam. Again, that's all on the calendar and schedule. But you don't have to worry about homework this weekend or anything. You can, if you want, focus on your retake. Also, the university offers services, so I'm going to take them up on it. I think it's a great resource. Let's see, they said they would open it February 19th through the 24th. So starting next Tuesday, you can expect or look for an email to your official university. You know, the one that's your university ID number at utah.edu. An evaluation. I think there's just 4 questions on what you, how the course is going thus far. I like doing that. One, I always appreciated being able to do it as an audience member, but I get a lot out of it in case there's some good feedback. I can do more of the things you like and maybe less and improve the stuff you aren't liking. Now, I won't know who did it. That'll be strictly voluntary. You can do it or not. I would like to encourage you to do so because I get a good benefit out of it. And I am willing, if I see that over 80% of the entire class participate, because I can't see individuals, I just know how many responses there were. If over 80% of the class participate, I will give everybody some extra credit, if that's impetus for you. But that, in theory, will start next Tuesday, before we meet again. You might see the email. It's all online. It should take, 5-10 minutes. Okay. Questions? Okay.
What was the median score on the exam?
Median?
Have you corrected it? Have you figured that out yet?
I don't remember the median score off the top of my head. They have returned. They are posted in WebAssign. I think the average, or technically the mean, was, I forget, not counting those that didn't take it. Knock the zeros out, about 67%. you will see 2 scores online, one called Exam 2, what you got, and then Exam 2 curved. I looked at it and decided to give everybody 3 extra points. Because one advantage of the bubble sheets is I get to see what percentage everybody answered each option. And so I always go through every question and I look to see, and there were 3 questions where the majority was not the correct answer. Usually by far the majority is the correct answer, but then there's always the outliers. So I decided, oh, that means either I didn't teach you well enough, you didn't study well enough, or it was a confusing question. I'm looking at that. But what that means for you is you get 3 extra points. So the score you get for Exam 2 day is the curved one that you'll see on WebAssign, which then makes the average like 76 or 77%, right? And then C where an average is supposed to be. Anyway, so. Okay. I didn't notice until teaching through this time that this course, this book, has a lot of P's to represent things. We've had P for momentum, and then we had P for power, and then they give you P again for pressure. Usually momentum is a lowercase p. Power and pressure are an uppercase P. I'm sorry, that's the way it is. But anyway, pressure, what is it?
Are they going to run out of letters and start using the Greek letters?
Yes, eventually they do start using Greek letters, yes. I still remember the day I was in college and, well, back up. First I remembered when they stopped using numbers and they started using letters in algebra. We thought that was weird. But I still remember in the first lecture when a professor put on the board an entire equation and none of it was the Roman characters, English. It was Greek. It's like, oh, what have I gotten into? Anyway, pressure, what is it? Well, if you have liquid, solid, or gas, and they're applying forces on something, you guys should be very familiar with forces by now. But if you apply a force on something like this, as opposed to like this, or more obviously, would you rather get stepped on by me wearing my shoes standing on your foot, or if I was wearing high heels standing on your foot? You know there's a difference, and one hurts more.
Regular shoes.
Well, I prefer that myself too, thank you. Regular shoes. So area matters with pressure, and it's related like that. Well, that's the cross-sectional area. Regular shoes, the area is this big. With high heels, it's a lot smaller. And you see if the area gets smaller, for the same force, I don't change my weight on your standing on you, I'm the same weight. So it's the same force down. But the area over which it's exerted, if it's less, like high heels, then it exerts a lot more pressure on you. And you go, ow. Units for this are forces in newtons. Standard unit for area is square meters, which makes, they call it a Pascal. After the scientist biographied, is that a word, at the front of this chapter, Blaise Pascal. So 1 Pascal is 1 Newton over a square meter. That's not much at all. That's a really small unit. Here's a meter stick. So a square meter is, imagine a box that big. That's pretty big. And a Newton, I think an apple is more than a Newton. So the weight of an apple spread over that much area, it's kind of wussy. That's right, the book gave an example, like a dollar bill sitting on the table. That's roughly the pressure of 1 Pascal. So we usually deal with thousands of pascals, kilopascals. But that's the standard unit, and that's our guide to equation for pressure. That relationship with force and area. Here's a block. This block weighs, I wrote it down, 1,170 grams. So what's its weight? Remember, the weight is mass times gravity. Its mass is 1.17 kilograms. Gravity is 9.8 meters per second squared. And I figured that all out for you. So, just way of review. If it's that has that much mass, then it's 11.5 newtons. That's the force it exerts. If it's on this side, it's 20 centimeters by 9 centimeters. That worked out to be 0.018 square meters. Yeah. The side that it's pushing on is that. So the force over the area gives a pressure of 639 pascals, just to give you an idea. That block exerts 639 pascals of pressure on the table. Now, just by flipping it, what have I changed? What else?
More pressure.
More pressure. And I'll spare you, it's a smaller area, blah, 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 so
Less to divide.
there's less to divide, exactly. The area is smaller, and that makes it go to 1,420 pascals. Again, I want to emphasize, we didn't change the force. We didn't change its mass. We didn't change its weight. Just how over the area it's exerted. So just by flipping something up like that. I haven't calculated this one, but if you tip it onto the corner like that, even smaller area, you can see that the pressure goes up even more than it did the first time.
The problem is that it's not stable.
It is not stable, that's for sure. So, some other fun demonstrations with that. Probably my favorite one today, the bed of nails. Raise your hand. Has anybody laid down on one before? Have you? Did you enjoy it? Yeah, not that bad. Anybody ever wanted to? Because today's your day. Come on down. There's just a few tips as you come on up. We'll have you walk up here. And you see, you know this already. If you sat on one nail, it's going to hurt. I wouldn't let him do this if it's somewhat safe. But we'll ask you to get down carefully, though, like this, and ease yourself down at once. Some people, if you don't push your hand on it, that's a small area. And if you just sit, your bum's a small area. So the idea is to kind of ease yourself down. Oh, he's got a nice coat on, too. Oh, you might scooch this way a little so your head's not on the nail. There you go. That's good. Got a pillow for you. What do you think? Put your legs down. Well, yeah, especially with a jacket. Sure. Could you stay like that for a while?
Probably.
Yeah. And the reason this isn't puncturing the wazoo out of him is because we've increased the area. There's hundreds of nails. And so each one does not have to support all of his weight. We've reduced the pressure on individual spots. Now, if you're willing, we can put this on top of you. What do you think? And the weight of it. But it should be the same. It should actually be worse on the bottom, right? Because it has to feel his whole weight plus this. This is just feeling the weight of this. Now, let's see how willing he is. I won't force him. You want somebody to stand on top of you?
Sure.
No, you don't have to.
Let's do it. Why not? You're already down.
Here, we'll get somebody small. Well, somebody, oh, all right, thanks. You doing okay?
Yep.
I've done this So I wouldn't ask you to do it if I hadn't tried it out. She's coming down. I'll ask her to step up here. And then, don't worry, I'll guide her. Whatever you do, don't jump, okay? Just go all the way up. And we're going to ease one up here, but push on me. Ease slowly, slowly, slowly. Now go ahead, go ahead. You're good. There you go. And back down, we won't kill him. Very good. Careful getting up. That's where usually people scratch themselves accidentally.
Yeah, they sit up on their butt or something.
Yeah, whoop. All right. Give him a hand. Another one. These are real nails, you know. On the clay. So two things were going on. One, all that weight of him, the block, and you were distributed evenly over the nails, well, fairly evenly. But also, when you stepped on the top, your weight wasn't all in one spot like your feet. It was spread over the top board. So that decreased the pressure on the top also. And I don't know if I'd want to sleep like this, but that didn't really hurt, did it? And actually, you didn't feel any more than it had she just stood on you, or laid on you. Or you could put a blank board on top of you and have her stand, and that's what you were feeling. But the nails just make it more dramatic, but it was the same effect. Okay, let's cover these up before I accidentally cut myself.
So you don't want to fall on it.
No, you would not want to fall on it. And yeah, unfortunately, some people, when they've gotten up, they've kind of slipped, and they have cut themselves. These are real nails. If you get too much force, weight on one spot, yes, it hurts. Since all of you didn't get to experience it, here's my mini version. And if you put this balloon there, watch. I can push on it. Is it going to pop or not? The answer is both. I push on it. Watch how much I get to push. Pretty significant. I have to up the force quite a bit to make the pressure large enough to pop the balloon. But if you're just on one nail, the balloon pops like that. So cover that one up too. Safety first. All right. You guys should understand pressure pretty well now. That's what it's talking about. So, right. This is brand new. You got the point now, but the first time I've done it. I used to do it with light bulbs, and I wanted to try it with cups. So if you want to try it at home, because I know everybody has their own bed of nails, but maybe you have a thing of cups. How many is this? 24 cups. Scoot you back. What do you think? Paper cups? I did it on 3 light bulbs once too. Again, if you spread it over a big enough area. We could calculate this, couldn't you? The area of the cups, you could add all that up. You know my mass or weight, or yours. You can figure out the pressure. Now, let's get rid of several. Because you want it to happen as much as I do, don't you? 4 cups. Same weight, a lot less area. Oh, well. And yeah. It's fun doing it on eggs too. It's just messier to clean up. Okay, Next thing you need. Density. A term you've heard before. Outside of science even. We'll use a D. This is the, usually in science, they represent it with a Greek letter, rho, which looks like a P. So for our sanity, let's use a D. And that is proportional to mass and volume. This is volume, big V. Not velocity. And so its units will be kilograms for mass. Volume is cubic meter. And that doesn't have a fancy shortcut name. It's kilograms per cubic meter. Often you'll see tables listed as grams per cubic centimeter. Or you might have heard of grams per milliliter. 1 milliliter is a cubic centimeter. But anyway, that's the standard units. And there's a table of densities of various things in your book, but in chapter 12, back when they talked about solids. It's on page 215 if you want to note it. 215, chapter 12. You can look at a list of densities. So this is going to guide our thinking. And, well, yeah. Let's take this piece of paper. It has a certain mass. It takes up a certain volume, so it has a certain density. If I go like this, the paper itself, how is the density different? It's a sort of a trick question. The paper hasn't changed. It's still paper. Paper still has the same density. You just changed its shape. That's a lot like a ship, a boat. It's made out of iron. You can, I guess I should have started like this. You can take a chunk of iron, and if you open it up, it's still iron. It's made of the same stuff. It still has the same mass. So it itself has the same density. The material does. But the boat itself might take up this volume, right? If you're looking at the paper and the space around it, think of it as a ship, a boat. This volume's bigger than this volume, right? This would be a much smaller ship. And so there, the density of the ship changed. It still has the same mass, but we changed the volume. And that's why a big iron ship can float. We're going to get to that more later, but it has a certain amount of mass, so it has a certain weight pulling down on it. And you're trying to make it float. Well, this doesn't have enough volume for that given mass. Open it up, and now the ship can take up a much bigger volume, and what happens to the density? It decreases, and the thing can float at some point. Does that make sense?
So it depends on but it depends on the body of water, too.
Yeah, whether it floats or not does depend on the body of water, the fluid that's surrounding it. That's what this chapter is going to cover more about, yes.
Is weight density and density the same?
Yeah, that's one term I wish the book hadn't used. They used the term weight density. I don't like it. Where do you first do that? 2:30, thank you. I'll make it clearer in a moment, because I was going to give you that formula in a different form. And that way, I think it'll make more sense then than telling you now. That's the next thing I'm going to do after clicker questions. Let's see if you got this density thing, because it's very important for the rest of the chapter. Oh, yes, I like to have fun. Okay. Okay, the session ID is down at the bottom. Polling is open. Basically, did you compare the density of water with ice? Water expands when it freezes. So how does that affect the density? Does it make one or the other more dense, less dense? Doesn't matter. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Most of you think water is. Okay, picture an ice cube. An ice cube. Picture a bucket of water. I want to start with the water first, a certain amount. If the whole thing freezes, does the mass change? I'm hearing a fairly universal no. Okay, so mass isn't changing. Did the volume change? Bigger or smaller? Bigger. So if density is mass over volume, and the volume got bigger in the denominator, what happens to the density? It goes down. So water is less dense. So ice is less dense than water. Does that make sense now? And that is why ice floats, because it's less dense than the water it's in. Okay, polling's open. Which weighs more? A liter of ice or a liter of water? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, we got the same number of responses as last time. Okay. Which one takes up more space? Water or ice? Ice. So if you confine them both to the same volume, 1 liter. You have 1 liter of water and 1 liter of ice. You can fit more water in a liter than you can ice because ice expanded. It's less dense. So it takes up more space for the same amount. You with me? So if you're cramming them both, restricting them to a liter, the same volume, you can't fit as much ice in because it expanded. So it'll weigh less. The water, a liter of water would weigh more because you can fit more of it in a liter. That one's a little more confusing. You guys good? Questions? So this is really emphasizing in these 2 chapters, mass and volume are different things. Weight and volume are different things. And you're going to have to pay attention, start now, when you read the chapter and listen to me and look at the homeworks. Which one matters? Mass, volume, force, pressure? Because they're not necessarily all consistent. Depends on the situation. And in this case, the volume's the same, but not the mass. Okay? Polling open. Which has the greater density? 100 kilograms of lead or 1,000 kilograms of aluminum? So now we're talking about density, and that's the ratio of mass to volume. So I'm not asking about mass. I'm not asking about volume. I'm asking about the ratio. 10, 9, 8, 7, 6, 5, 4. Well, that was the same that we've been getting, so I'll just stop now. Lead is more dense. That's like, lead itself is more dense than aluminum. So it doesn't matter how much or little of lead you have. Lead is more dense. It's just the way the element is formed. So, sort of trying to fool you. 1,000 kilograms of aluminum, well, that's more. Okay, so you have more mass. But aluminum has a certain density, period. It doesn't, if you add more aluminum to it, it doesn't change the aluminum. It's still aluminum. And it's still less dense, always less dense than lead. How you feel about that one?
Does that mean that you're going to have more inertia?
If I have something that's more what?
If there's something that's more dense, does that object have more inertia?
More dense. Not necessarily, because if it's more dense, that means the ratio of mass to volume is greater, larger. Inertia is only based on mass. So if the reason it's more dense is because it's more mass in the same volume, then yes, it would have more inertia. But if it's the volume that adjusted, you still have the same amount of mass, which wouldn't change its inertia. Do you follow that? I think I have one more I wanted to ask. I'm confident you'll get this one now, I hope. What's more dense? 10 kilograms of water or 1,000? Or they're the same? Ten, 9, 8, 7, 6, 5, 4, 3, there they are. You're right. They are the same density. It's water. So it doesn't matter how much of it you have. It's still water. Now, if it was seawater, that changes things. Seawater is a little more dense. But I didn't ask that. So, oh yes. Uh-huh.
You're talking about the boat taking up more area. So what if you had like 100 kilograms of lead planned out like a boat, and then
Yeah.
whatever it was.
If you talk about a ship or a boat made out of lead versus aluminum, yeah, that wasn't asking about the density of a ship made out of it, which takes up more space than the lead itself. So that was like differentiating between the paper itself, the material, or what it's making or forming, the ship. And there is a difference. So lead itself is like paper. I can add more paper to it. Thanks, Rachel. That didn't make the paper any more dense, because it's still paper. But the notebook, I can adjust the volume of that and change the density of the notebook. It's paper in the space it contains. A ship, when think of it this way, if you just put a block of iron in the ocean, it sinks, you know that. But if you spread it out, it's going to displace not only its weight, but the space it takes up. And so the density of the ship is not just steel anymore. It's steel and everything in it and the space it takes up, which is important.
So on this question, what I did, because density is mass over volume, is I just used 10 as my volume. So I did 10 over 10, which is 1, and then I did
Okay.
over 10, which is 10.
Okay, so you fixed the volume.
Right.
And so in your case, if you take 10 kilograms of water and shove it in 10 liters of space, and then take 1,000 kilograms and shove it in the same amount of space, the density of that container would be larger. Thing is, you can't cram 1,000 kilograms into a liter, though. That's the thing. So with this question, as stated, in order to have 1,000 kilograms of water, it will take up more space. So in order to have the same density, yeah, A will take up less space, B will take up a lot more space. Do you see that? So rework these, rethink about these. You're going to have to ponder on these outside of class, because it might make sense when I'm talking, but can you do it on your own? There's good examples in the text. The text is great. That's why I chose it. Because this seems more confusing to folks, I find, than other stuff. Yes?
So as long as, like, if it's a problem like this one, as long as they're the same component, it doesn't change the density by how much mass you have. But if it's two different, like the aluminum and the lead, they would have to take into consideration which one's more dense.
Yeah, but between lead and aluminum, they're different materials. They have so much matter packed in a certain amount of space. So they come with fixed densities. Lead can cram more mass in a smaller space. So it's more dense, period. So it doesn't matter if we add more lead, it's still lead.
Well, if you like change the molecular shape of the lead, wouldn't that affect the density?
If you change the shape of lead, that means the atomic structure changes. Yeah, you can do that, and you know what happens? It becomes gold, and you're an alchemist. If you change its structure, you've changed it chemically, and it becomes a new element with a different density. And you wouldn't be out. Nobody's been able to do that yet. So, although my family's into Merlin at the moment, and they got some alchemists on there with magic. Okay, put your clickers away.
Well, I think it's interesting to know that with water, someone like me can go scuba diving. There's pressure on me, but I thought it was interesting that when someone's scuba diving, there's more pressure. Because I'm small in relation to the water I'm in, that's why there's that water pressure that we talk about.
Great lead in. That's where I'm going next. Pressure with depth. He goes scuba diving. And interesting that he's small, so there's lots of pressure on him. The deeper you go, there's more pressure. But that's because there's more stuff on top of you. And that's what I want to do next. Pressure with depth. We'll get to that weight density thing. If these are water molecules stacked on top of each other, you're just taking like a vertical slice as you go underwater. Here's the surface, let's say, up top. And down here's the bottom. Well, all these water molecules have mass. So they have weight. So they exert a force. And what do they exert a force on? You, with a certain area, down here at the bottom. And force over area is pressure. So the more water you have on top of you, the greater the force. More force over your same area increases the pressure. So the pressure increases when you go deeper and deeper in water because there's more stuff stacked on top of you, pushing down on you. You can see that with this. At the bottom here, see how they're closer together? The springs are feeling more pressure down there than up top where they're farther apart. You can flip it over. That one got stuck. And again, up top they're farther apart because they don't have to support as many molecules on top of it. Where down here they do. So pressure with depth. Whoop. Getting ahead of myself. Some of you have expressed to me you're mathematically minded, so watch this. That's pressure. It's the weight of the thing, so mg. It's gravity that's pulling it down, so it's its weight. You can write mass in terms of density. Mass is density times volume. Do you see that with this formula? Just rearrange the density formula I wrote earlier. You can represent mass in terms of density and volume. What I want to do is volume is area times height. Do you remember that from your geometry? Say you have a cylinder. And if this has a certain area and you want to know the volume of that container, you multiply that area by how tall it is. And you'd get the volume. So that's all I did there. The A's cancel the area, and you're left with that. Pressure is density. I always like writing it this way. So it's the same formula. I just substituted density in for mass and rearranged because this is very useful. The pressure you feel in a fluid is based on the density of that fluid, because if you're underwater, you feel more pressure than you do with air on top of you. Gravity, because that's what's accelerating it down. And how much on top of it you have, or how far underneath it you are, the height. So you can figure out the pressure when you go scuba diving with the density of water, gravity, and how far down you are, your depth. You know exactly the pressure in pascals. What I find most interesting with this is that pressure is depth dependent. That H. It's not volume dependent. So the area went out of it. It doesn't matter how wide it is. So if you're down underneath the water here, you're going to feel the same pressure as your friend over here at the same depth. Because they have the same stuff on top of them, above you. The stuff over there isn't pushing on me, and stuff over there, but this is. I have this example to show that. I call it Pascal's vases. Well, I don't. That's what it's called, after Pascal. And right now there's so much water in this reservoir over here, the big one. I'm going to open the valve and allow the fluid to flow into these different shaped vessels. And without making it a clicker question, which one will be the highest? The water level will come up the highest in which one? The skinny one, the straight one, the wiggly one, or maybe it'll stay highest over here? So we'll do it. It's open. It takes a bit. It's filling up. Water's coming up. Can you see the blue okay? To help? So they're the same height. That tells us that the pressure down here at the bottom of each one must be exactly the same, because it's pushing the water up to the same height. And that's exactly what this all means. They're both the same depth. It's water, so they all have the same pressure down there. So it wouldn't matter if you were scuba diving here, 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 or here, you'd feel the exact same pressure. And think of it this way. Which would you have to build stronger? A dam that is blocking the entire ocean, or a lake? Let's say you're 100 meters down on the dam. 100 meters down. Which one will have to be stronger? Holding back the whole ocean or a lake? And you would say the ocean, don't you? Because it seems like it's got a lot more to it. And this is where I emphasize pressure is not volume dependent. So it doesn't care that there's a whole ocean there. It cares that it's 100 meters down. So does the lake. So it would be the exact same pressure on both dams, 100 meters down. Even though there's way more water behind the dam, it's still at 100 meters down. That means this is how much matters at the pressure there, not all of that next to it. You with me? That's why these all go to the same depth. This has a lot more water, Don't you think it'd be heavier on you down here? No, it's the same pressure there as it is on the skinny one, because you have the same amount of water above you at that point. Depth dependent, not volume.
Why is one of those more blue than the other? Bluer than the other?
Why is one more blue than the other? This one is thinner, so light shines through it and it looks lighter. Where this, it has more to go through. Here I have a bottle.
So it looks like the
Oh, I'm sorry.
same idea, right? Like the ocean?
Similar idea to the ocean. There's some optics going on there that we will study. I have a flexible tube here, more blue water. And what I want you to see is you can use this as a barometer. The height of the fluid in the bottle is the same as the height in the tube. Because why? Air is pushing down here and air is pushing down here. It's the same air. So they're feeling the same pressure. So they come up to the same level. If I lower this tube, look, the fluid still only comes up to the same height. It's at the same pressure at those two heights. You can even raise this up first. And magically, the fluid can go up, but it goes back down, and it settles, though, at the same height. Water seeks its own level because of that relationship there. There's one of these pump caps you can buy to keep the fizz in your carbonated pop. So now I seal the bottle off. And I'm going to increase the pressure inside the bottle. That pressure is going to push on the surface of the water and increase the pressure in the bottle. And the fluid goes up. How much did I increase the pressure in here? Well, the difference in this height. How much higher it went up. What's the pressure this amount of water, this column of water exerts? Well, the density of water is known. Gravity is known. You just measure that height difference, right? It's that tall. So the pressure down here, due to this much water above you, exerts so much pressure. And that pressure is going to exactly equal the amount I increased over here, because it's holding it up.
And if it were soda, there would be more pressure, of course.
There would be more pressure. If I, loosen this. There we go. It can fall back down. Here's another one. This is called a Marriott's flask. It looks like this will be the last thing we do. More blue fluid. Lots of food coloring today. I like blue. It shows up better than the others without having to use as much. This flask has 3 holes in it that I've plugged. Yeah, good point. I should use red. But I have to use more of it, so I went with blue. We're an equal opportunity school. We just shoot Cosmo, that's all. So there's 3 holes here. I'm going to unplug them. Doop, doop, doop. Water will shoot out, you know that. But how do you think the water will shoot out? Exactly the same? No. Tell me what you think. Very good. This one, I hope you expect the water will shoot out further now. Because who's under larger pressure? Here, here, or here? Down here. So the increased pressure will shoot it out with higher velocity. Okay, I'm sure I'll make a mess on this. That's why I got my sponge. But here goes. Let's start with the top one before it runs out. Then the next one. A little further. And the last one. Shoots it out the fastest. It's projectile motion. Whee! And you can see as the height decreases to this hole in the middle, it shoots it out less and less fast because there's less and less pressure. Now we'll just set it there and let it finish. Ooh. This is cool. the velocity that comes out there, you can do energy. Think of the potential energy of a pocket of water. It falls whoosh, that far. Where does that energy go into? Kinetic energy, and it shoots out yay fast. The more potential energy it had, in other words, the higher up you started, the higher the pressure down here, the faster it shoots out. It relates. Any last minute questions? Well, have a great long weekend then.